So we looked at the linked list problem, which involves finding cycles, and I'm going to link the video somewhere on the screen. You can check it out. That problem involved 2 pointers, and I'm going to show you exactly why this one involves 2 pointers as well, and how this approach of 2 pointers is very versatile, and you can actually use it in a lot of different problems, and you can save yourself a whole lot of time in terms of linear scans. So let's talk specifically about what this problem entails. So it's a standard linked list setup where you're given an input linked list, which it's an arbitrary length. You don't really know the length ahead of time. All you're really given is just the head of the linked list. So the task for you is, given a certain number k, you've got to find out and delete the node which is at the kth position. Now this is very simple if it's the kth position from the start of the list, because you can just linearly traverse from the start and you can rewire the linked list and you're done. The tricky part is this k is the number, the order of the node from the end of the list. So this complicates things, because if k is equal to 1, effectively you've got to remove the last node. But you don't really know where the last node is ahead of time because you only have the head. So let's talk about the naive approach. Naive because it doesn't really add anything to our understanding of linked lists. All we could simply do is we linearly scan through the linked list. We just go through the whole thing. We count the number of nodes that are actually in the linked list. We store this number. Then we, in a way, figure out n minus k, which gives us the node's position from the start. So in a way, reframe the problem to be deleting a node from the start instead of the end. This is doable. You could do this. It's where it's gonna at worst take order of n time. Really, you just have to do this twice, right? Because you got to go through the whole thing once, and then worst case you might have to remove the last node, so you got to do the whole thing again. So worst case, it's still a linear scan, order of n time, not super bad really in terms of time complexity. But it's boring. It's really not the solution that interviewers are expecting you to code up, because it really adds nothing to the structure of this problem. So let me tell you what the accepted solution is, which involves 2 pointers. The approach is you have a fast and a slow pointer. The terminology will be familiar because we call the pointer that moves ahead fast and the pointer that is behind slow. Similar to the problem that we saw earlier, which is the linked list cycle problem. Same approach, except in this case, we are not gonna start with a distance of similar approach. A few changes in why we need a fast and a slow. Remember, our goal here is to find and identify the node that is k units away from the last node. So we don't really know ahead of time where the last node is. This problem is one of those problems where all you have to really do is think about the end condition and then backtrack. I don't mean backtrack in the sense of programming, but rather think from the end and then look at how to get there. Ideally, when we're at this point, we should be able to do some constant operations and then remove the node that is k places from the end. Imagine our fast pointer is here and our slow pointer is here. So fast pointer is at the last node of the list. The slow pointer is exactly at the kth node from the end of the list. This is a great place to be, because all we really have to do now is remove the node that the slow pointer is pointing to and rewire this setup in such a way that the linked list is still intact, and we're done. All we've done is one linear scan, and it'll be great if we can achieve this. So how do we get here? Because remember, our fast and slow pointers, they're going to start at the head of the linked list. So what kind of initial setup can we do for these fast and slow pointers so that we achieve this particular configuration? Let me say straight up, the earlier problem that we saw, the linked list cycle, the fast pointer always moves twice as fast as the slow pointer. This is not a great setup for this problem, because remember, we want to have exactly k distance at the end of our problem, which means we want to achieve a constant number in terms of distance. So if we're going to do some sort of exponential increase, we can't really know ahead of time if we can maintain this distance. So one way to think about this is, what if we set the slow pointer to be at the head and the fast pointer k units ahead? We start with this distance ahead of time, and then we always maintain this distance. As we move the fast pointer one up, we move the slow pointer also one up. So there's no multiplicative factor, but there is an offset. So ahead of time, we set an offset equal to k, right? This is one way to do this. And we would achieve this end condition where the fast pointer reaches the end node, and this is identifiable because the end node is the only one that points to null or none as its next node. So this is the condition we're looking for. So if all that makes sense, let's pause and think about whether this is actually useful for the step 2, which is rewiring the linked list in such a way that it's intact, which means we have to remove this particular node which is pointed to by the slow pointer, and then we have to point the previous node from the slow pointer to the next one to the slow pointer. This is tricky because we can't go back to this when we are already here. So it might be better to actually start with an offset of k plus 1. Why is this useful? Because we now can achieve a situation where our fast pointer is at the end of the node, but the slow pointer is actually one before our destination or target node. And this is good because now it's a constant operation to point the node that's currently pointed to by the slow pointer to the correct node, which is next dot next, right? You can do something like this. You can always look ahead in a singly linked list, but you cannot look behind. So this is very important. So the offset being k it's going to make things trickier, and making it k plus 1 is actually a lot easier for us. And the reason this works is because we are always maintaining this distance as k plus 1 right from the start. So that ensures that when we reach the end of the node, we are ready to do that single constant operation to rewire our linked list, and we're done. It's a single scan. It's still order of n time complexity, but it's a lot cleaner in terms of not having to do 2 scans.